Okay. So welcome everybody. So this is the afternoon session of the Introduction to Python workshop for fall 2020. The first offering of the Introduction to Python workshop. There'll be another offering later this semester in either late October or early November. I can't exactly remember the date at the moment. Welcome. We're going to pick up where we left off on the morning session. So we're going to start in with kind of a basic introduction to Pandas, and then we're going to do some plotting with matplotlib, and then we're going to start using some more advanced kind of Python language features. So without further ado, well, actually, I should say for anybody who is just joining for this afternoon, you didn't either because you couldn't make it to the morning session or whatnot. So my name is David Pugh. I'm a staff scientist at the CALS Visualization Core Laboratory. I'm joined by my colleague, Glendon Holst, who is also a staff scientist in the Visualization Core Lab. This workshop, the Introduction to Python, is part of our Introduction to Data Science workshop series, where we cover kind of the foundational tools, Bash, Shell, Conda, Python, Git, and SQL, that are kind of the core tools used by data scientists and machine learning researchers and practitioners. And the idea is to try to build kind of a skill base in these core, build capacity here within CALS primarily in these core tools and skills so that we can enable more advanced machine learning and data science research here at CALS. So thank you for joining us. Today we're going to be doing a mix of hands-on and lectures, just like this morning. I want to thank our colleagues at the Research Computing IT for putting together a fantastic BinderHub implementation here at CALS that is allowing us to scale this training quite substantially within the CALS community. And then I'd also like to thank the BinderHub Federation for continuing to provide free access to a BinderHub for anybody around the world who wants to participate. And that really allows us to kind of scale this kind of training to people outside of CALS here in Saudi Arabia. And I think through Professor Jerry's course, we have a number of people joining us from not just here in Saudi Arabia, but other places as well. Okay, so with that little intro, I'm going to go ahead and start sharing my screen again, and we're going to get to work. Okay, so let's talk about what we're going to cover. As per usual, I'm well behind on my estimated schedule. So we are going to pick up with working with Pandas. So we're going to learn how to read data into a data frame, and then we're going to do some statistical analysis with that, and then we're going to do some plotting. And then we're going to hop into kind of learning to apply more advanced Python language features like for loops and conditionals, using this kind of data analysis workflow as our motivation. And then towards the end of the day, we're going to write some custom functions and talk about some best practices for Python programming. And then we'll try to stop and have a Q&A and wrap promptly at about 5. So with that, let's go ahead and get started. And as always, again, for questions, if you want to unmute yourself and interrupt and ask a question, feel free to do that at any time. If you want to write your question in Slack, or not Slack, sorry, in the chat, you can do that as well. And otherwise, I guess we're good to go. So any questions before I jump in and get started with the teaching? No? Okay, cool. All right, so here we go. So reading tabular data into data frames. So the main outcome of this episode is, unsurprisingly, to be able to read a CSV file into a Pandas data frame and get some basic information about the data frame and just kind of understand that process. So Pandas is, I guess I can bring up Pandas. So Pandas is one of the primary libraries for doing data analysis in Python, particularly CPU-based data analysis. It's the design and structure of Pandas. The API of Pandas has been very influential. So just learning Pandas will set you up well if you want to start using more advanced libraries for doing GPU accelerated data analysis. Many of them have adopted the Pandas API because of its influence and popularity. There is an excellent book by the Pandas creator, or one of the Pandas creators, Wes McKinney. It has a second edition that was just out in September or August of last year. So it's a pretty recent version of this book. I would highly recommend it if you really want to do a deep dive into Pandas. Okay, so the first thing we need to do is we need to import Pandas. Just like we were importing libraries this morning, we need to import Pandas if we want to use it. The canonical import for Pandas is to import Pandas as PD. So the alias PD is how we'll refer to everything from within Pandas. So again, if we hit Shift-Enter to execute that, that tab, then what we can do is now we can import our data set. So Pandas has this read CSV function. We can take a look at the docstring for this read CSV function. As you can see, it's quite involved. There are an enormous number of arguments that you can pass into the CSV function, read CSV function, and customize its behavior. We'll only touch on a few of them today. All of them are optional, and all of them have sensible defaults. So typically, the best place to start is just to try to pass in the path to the file that you want to read in, and then and see if that reads in or see if it throws an error. So first, we need to figure out where the data files that we're going to use, that we're going to read in, live. So our notebook is in the Introduction to Python Notebooks directory. Our data is in Introduction to Python Data directory. So the path from our notebook to the data directory means that we need to go up to the parent directory. And so those of you who attended the bash training will remember that this ... is a shorthand for a reference to the parent directory of the current directory. In that case, it's a reference to Introduction to Python. And then we need to traverse down into the data directory. And then we want gapminder GDP Oceana.csv. And we are going to assign the value that is going to be returned by this function to data, the variable data. And so now, if we hit Shift-Enter, we get a file not found error. So that means that I either got the path wrong, or more importantly, I mistyped the name of the file. And I spot my typo right there. I misspelled Oceana, and there we go. So once we've loaded the data, we can actually just print the data just to see what it looks like. And what we can see here is we have the data has two rows, given arbitrary numbers, or not arbitrary, but given row numbers 0 and 1, and a country column, which has values Australia and New Zealand, and then GDP per capita for years 1952, 1957, so basically every 5 years starting from 1952 and going to 2007. Now, if you don't have an economics background, you might be a bit unfamiliar with what GDP is and what GDP per capita is. So GDP stands for gross domestic product. It's basically a number that measures the amount of stuff that a country produces in a particular year. And per capita means per person. So it basically divides by the number of population, or the amount of people living in that country. So it's a statistic that is normalized by population. And there's quite a lot of subtlety into measuring, how much stuff that a country produces in a particular year, as you might imagine. In particular, there is change in the value of money across time, inflation or deflation. And there's also issues with purchasing power, that if you're going to compare different countries in terms of how much stuff they produce, you have to take into account the fact that, say a US dollar in the United States will buy a lot less stuff than a US dollar in, say, Nicaragua, or Myanmar or someplace, or some other country. So these numbers that we're going to look at have been appropriately adjusted to take into account the fact that there is inflation or deflation within a country across time, and across countries at a particular point in time, there's different purchasing power. So this is what's called purchasing power parity, real purchasing power parity, GDP per capita. So it adjusts for all of those things. Okay. So also, because we're in JupyterLab, we can actually navigate to the data directory and inspect the CSV file directly. So we can open a CSV file, as long as the CSV file is not huge. If it's huge, you might inadvertently crash your JupyterLab server. And by huge, I mean like many gigabytes of or more. But here it's just a small CSV file, and so we can kind of inspect it and see what's going on here, things like that. Right, okay, so I just wanted to remind you that in JupyterLab you can do interesting things like that. Okay. So let's talk about one of the important options to the read CSV file. So if you look at this file, this data set, the natural index is not this arbitrary row numbers that Pandas has given it, but it's actually this column country. So if the data set has a natural index column or columns, then there is an index call argument, which you can pass in, and then you can provide, there's several ways that you can define the index column. The easiest way is just to put the label, the header for the column or columns that you want to be the index. And if you had multiple columns to create an index, you could put them in a list. But here we only have one, and I'll go ahead and put them in square brackets just to indicate that we could have more if we wanted. And so if we evaluate this, and now we look at the data. So now you can see over here we have the country column has been offset and is now listing Australia and New Zealand as the index basically for the data. So that's usually the first thing that you want to understand about the data that you're working with is how is it indexed? What column or columns uniquely determines the other values in the row. So here, basically, once we have indexed on the country, then these other values in the row correspond to values of GDP per capita for that country. If you had like a country and then a region, like some sub-region within the country, then you could index on both country and region, and then the rest of the entries in the row would correspond to the GDP per capita for that country and region, or for that region within a country, rather. Okay, so you can get some information about a data frame. There's a .info method. And if you run, execute this, you can see the number of columns, so, and their names, how many values are not null. So basically these are the number of values that contain data. And because we inspected the CSV file, we knew that each column has 2 values and that none of the values are missing. There are no holes in this table or anything like that. So that's why we see 2 all the way down here. And they're all, it says float 64. So that's the data type. When we talked about data types this morning, float 64 is a 64-bit floating point number, and that's the kind of the largest or the highest precision kind of floating point number that you can represent on a 64-bit computer. And that's just the default floating point data type that Pandas sets. Okay. The data frame has a columns attribute, which stores information about the column. So here it basically returns an index, which basically gives you the name of the columns and their type. Now the type here is object. Object is kind of a generic data type and is what you will get in Pandas if you're dealing with any non-numerical data. In this case, these are all strings. Okay. So you can do all kinds of stuff with data frames. In particular, you can transpose a data frame, which will swap the indices. So if we were to do print the transpose of our data, now we get a long data frame where the index is the GDP per capita in different years, and then the columns are the countries, Australia and New Zealand. So this is kind of a simple reshaping of the data. If we wanted to do some descriptive statistics on our data, there is a describe method. And this data.describe method computes mean, standard deviation, min, max, and the interquartile range and the median for all of your columns. And since these are all numeric columns, it can compute all of these numerical statistics for each column, and then it just gives you all of these things. So we could go through here and see if there's anything interesting to note. So standard deviation is kind of a really reduced form measure of how much spread there is in the data between kind of the richest and the poorest countries. And you can see that generally this figure or this number is trending up over time. So under that metric, that's like saying that the spread in the GDP per capita is increasing over time. Possibly inequality is increasing over time. Okay. Now the rest of this episode is exercises. So I'd like to set aside 5 minutes for you guys to go over the exercises. So try reading in a different CSV file. So there's a CSV file for each continent, I think, and then there's a CSV file, let's get rid of that, in the data directory. So there's a gapminder all, which has data kind of for all countries combined, and then there's different ones roughly by continent, but not entirely. So go ahead and get practice reading in the data, learning a bit more about some other operations, head and tail, that you can do with data frames. This one is a thought experiment just to get you to understand how to access a file, to make sure you understand the concept of a path and how to correctly access this CSV file from within this notebook. And then an experiment with writing data. So there's a read CSV. There is also a toCSV function, which allows you to write a data frame out to a CSV file. So you can get some practice with that. So I'm going to set my timer for 5 minutes and give you an opportunity to take a look at those exercises and then ask me some questions. And any exercises that you're uncertain about, we can go over them together. Otherwise, take a look at those exercises and we'll be back in 5 minutes.
Mr.
Yes.
When I import the pandas at PDF and I wrote the same function, I receive an error like file not found error.
The file not found error. Okay, so let's, so the file path, let me share my screen again. Okay, so the file path that you need to use is a little bit, well, it could be different than what I have here. It depends on where you have stored your notebook that you're using. So, for example, the data directory. So inside Introduction to Python, so the data directory contains the CSV files. So what directory contains your notebook?
To go to the notebook.
That's the first thing to figure out.
So I have to go to the notebook first?
Well, it depends on where is the notebook that you're working in. Where is it? On the left-hand side of Jupyter Lab, you have this file browser. So where is your notebook?
It is in the notebook folder.
It's in the notebooks folder. Okay,
yeah.
That's just like mine. So then this is the path that you will need. So this ... basically is a reference to the Introduction to Python directory. And then from there, you travel down into the data directory, and from there you can find the name of the CSV file. So this is called a relative path, because the path that I'm passing in is relative to the location of my notebook.
Okay, let me try this one. Yeah, I got it.
Okay, good. So that's important. So if anybody's having trouble getting the data set loaded properly, just pay close attention to the path. And if you're still having difficulty, or you would like, I can send you off into a breakout room with Glendon, and he can give you more more kind of detailed help and instruction on getting the data read in. Okay, so does anybody have any particular questions about these exercises? Is there any of these exercises that you think we ought to go through together?
Yeah, so I have a question.
Yes.
Because in the exercise it tells you how to get the first two or the last two or three or whatever.
Uh-huh.
What if I want to check data in between, like the 5th row or the 6th row?
So that's a great question. So we're going to come to that in the very next episode, which is going to cover basically slicing and indexing of data frames. So I will postpone answering that question until we get to the next episode.
Okay.
Any other questions about these exercises or anything about getting the data read in? Okay. So just to summarize the key points, so Pandas is the library that you want to use to do basic data analysis with tabular data. You can use the index column to specify kind of what column or columns values should be used as the row labels. And then, of course, the column labels will come from the header of the file that you're reading in, the CSV file that you're reading in. And we talked about these different methods that you can call to do things with the data frame. We're going to see a lot more of those in the following episodes. I guess the big thing is making sure that you understand the path to the data that you want to load, basically, and how to get there from where your notebook is. That's the trickiest thing about reading CSV files. Okay, so Pandas data frames. So we're going to talk about doing statistical analysis on tabular data. And we're going to answer the question that was just posed, which is basically how do you select either individual values from a data frame or entire rows or columns or subsets of rows and columns? And how do you subset data based on some kind of maybe like a Boolean conditional? How do you filter data in a data frame? These kinds of things. Okay. So so here we go. So a Pandas data frame, Pandas kind of has two core data types, a data frame and a data series. And a data series is basically a column of data with row labels. And a data frame is a collection of data series that have a common set of row labels, basically. So you can think of, from a CSV file, you have some row labels, and then each column in the CSV file is a series, and then the collection of all the series is a data frame. Now, Pandas itself is built on top of the NumPy library, and so it borrows and builds on a lot of the functionality from NumPy for manipulating numerical arrays of data, and then just makes that more user-friendly for a data analyst. Okay, so let's load some data. So I'll call this Europe. Or should we do Europe? Let's do let's do a different. So in the notes, in the teaching materials, we use Europe, but I think we should do Asia. So we're going to read CSV, and then we're going to use the same path, and you can use the same pattern as above. It's just gapminder, GDP, now Asia instead of Europe, CSV. And the index column is going to be the country. Okay. And now we can look at, so one of the exercises in the previous episode had you use this head method, which returns the first 5 rows in the data frame. So here we can just inspect the first 5 rows to make sure that the data loaded properly. So we have Afghanistan to China, and then we've got our GDP per capita across the columns. Okay, so that looks pretty good. We can also inspect the last few rows, tail, using the tail method. And so this is the last 5 rows. We've got Yemen and then Taiwan. And so we can scroll through here, and yeah, everything looks good. Okay. Now we can do our info just to look. So now we've got 33 rows of data. There's no missing values because all of the 33 non-null all the way across. We also get a memory usage here, which is can be interesting sometimes. It's for data sets that are small like this, the memory usage is somewhat trivial, so you don't have to pay too much attention to it. And the memory usage is tied in with the data type. So it takes more space in a computer's memory to store a 64-bit floating point number than it does to store a 32-bit floating point number, or a 16-bit floating point number, or an integer. So depending on how large your data set is, you might want to pay close attention to the data types that are being used to store each column of data, because you can sometimes reduce the memory footprint of your data set quite substantially by using appropriate data types. And this can change a problem that, this can take a data set that naively might not be able to fit in your computer's memory and make it into one that you can easily work with. So here, all of our data sets are sufficiently small, but when I work with students or staff or faculty here at KAUST or other kind of clients around the kingdom on data analysis and Python, one of the first things that I do is work with them to make sure that the data types are set appropriately to minimize the memory usage. It's really helpful when you have larger real-world problems. Okay, so the first thing we want to do is select out some data. So what if we wanted to select out this value of data here? So this is the value of GDP per capita in 1952 in Afghanistan. So how would we do that? Well, there's a few ways. The kind of naive way would be to select data by index, by integer index. And the way that you do that is using this iloc method. And you can put a question mark to get the help on iloc, and you get a whole bunch of examples and explanations as to how it works and things like that. But basically what you do is you use square brackets, just like you were indexing into a string, except now we're indexing into a 2-dimensional data frame. And so if we want the 0th row and the 0th column, which is, again, the row corresponding to Afghanistan and the column corresponding to GDP per capita in 1952, we can index by integers and select out that value. Let me, just so it's on the same, just so you can see. So here is the exact same value that we have here. Okay. That's really not the best way to select data from a data frame, because one of the features about data frames is that this isn't really just a 2-dimensional array of numbers. It's a labeled row and labeled column array of numbers. So we really should take advantage of the fact that we have labeled data when we are indexing. And the way that you do that is using the loc. Instead of iloc for integer locations, loc is for labeled locations. And here we can just put our label, Afghanistan and GDP per cap 1952. And I've already noticed a typo. And there we get the same result. So I generally avoid this method because the integer indices are kind of arbitrary. It depends on, here the countries are sorted alphabetically, but if they were sorted in some other order, then this would give you some different answer. Whereas this will always give you the value of GDP per capita in Afghanistan in 1952, irrespective of how the rows are actually ordered. So use this method instead. Okay. Now, we talked about slicing strings earlier, using the index notation for slicing strings. We can do the same thing here if we want to select like all rows or all columns. So if we wanted to look at, so let's see what countries we have. So maybe what we should do is do Asia describe. Okay, so this is giving us descriptive statistics for GDP per capita in the different years, but actually what I want is to find out what countries are in this data set. So one thing I could do is, remember we talked about transposing the data. So if I transpose the data and then describe, so now this is going to give me descriptive statistics for the different countries. And this is kind of what I wanted, was to scroll through here and see what countries are available. In particular, let's work with Saudi Arabia. So if we wanted to select from our data set the row corresponding to Saudi Arabia and all of the years, we can use a colon as a placeholder for everything. Basically, it's like select from start to stop, where we've not included start or stop, and so it includes everything. And I have a typo. Okay, so here is the GDP per capita in Saudi Arabia from 1952 to 2007. So that's all of the data for Saudi Arabia there. Okay, if we wanted to do, instead of a particular country across time, we could do at a particular time across countries. So if we did all of the countries, but a particular column index, so we could do GDP per cap, I don't know, 1957. 57. Then here we've selected out a particular column, a particular year, and the statistic across countries. Yeah, so you can see how I just use the colon to stand in for kind of all the data along a particular dimension. Okay. Suppose that we wanted to do multiple countries. So we could do, let's look at our Asia head. Let's look at the first 10 rows. All right, so what if we wanted to select all of the countries? Let's go a little further. Let's change this to maybe 15. Okay, so let's suppose we wanted to get all the countries that started with I. Well, here we could just do Asia. And because everything is sorted alphabetically, we could just do India through Israel. And then if we wanted all of the columns, we'll put a colon to stand in for all the columns. And then this will give us the data on those countries. Now, this is the fact that this returns India to Israel and includes only these countries has to do with the way that the rows are sorted, because it's kind of slicing like you would slice a string, with one exception. It includes the end. So it starts at India, the row labeled India, and goes all the way until it hits the row labeled Israel, and then includes both endpoints, and then selects out all the columns. If we wanted to collect only certain rows and certain columns, we could do that too. We could do GDP per cap 1967 to GDP per cap 1997. And then that selects out only those columns. So now you've seen how to kind of subset on rows and columns. So these, I've just been basically subsetting and printing the data, but you can actually use subsets in further computations. So we could call this subset, and then if we wanted to do subset.describe, then this will give us the descriptive statistics for just the countries that are in that data set, basically. So this is the average GDP per capita in 1967, averaged across the 5 countries, India through Israel, basically. And you could do, each of these little rows generally has their own function. So if you wanted, you could do subset max, and that basically gives you these values here. And similarly, there's min, and there's a whole bunch of others. Okay. So another way is, usually when you're working with data, you want to filter not on, you might want to filter on row labels or column labels, but you also might want to filter data based on some condition on the values in the data themselves. So for example, what happens if what if we wanted to find countries in Asia that had GDP per capita higher than, let's try 10,000 US dollars in purchasing power parity in a particular year. So let's see what happens if we do Asia greater than 10,000. Okay, so what has this done? So it has generated a new data frame of values true and false. So notice that the row labels are the same and the column labels are the same of this new data frame, but the values are true and false depending on whether or not the condition is true or false. So Bahrain in 1957 had a GDP per capita greater than 10,000 US dollars. And it has maintained that, it looks like, through the remaining years in the data set. Let's see, there's some other countries in here. Let's see if we can find, we see a lot of falses. So Kuwait, so another Gulf fossil fuel resource-rich country. See, so here's Saudi Arabia. So Saudi Arabia crossed that threshold in, this is 52, 57, so 1962, and then looks like it has maintained. So Singapore is a very wealthy country today, but it wasn't until, what column is this? 1977 that Singapore crossed the threshold of that GDP per capita greater than 10,000 US dollars. And then I'm sure there's countries in here that have never crossed that threshold, perhaps the majority of those countries. Okay, so how can we, so what if we wanted to select the actual data values themselves that satisfy this criterion. So we can do the following. We can take our, so we had our condition. So I will call, we can actually assign that condition to a variable. So if we had Asia greater than 10,000, and we call this let's call it, let's say that's is wealthy. And then we can do Asia. And here we can actually now subset the Asia data set using this, this criterion. Oop, must have spelled, I did spell it wrong. And so now what we get is any location where the condition was false gets replaced with not a number. And then any location in which the condition was true is replaced by the actual value from the data. So here we see the actual time series for Bahrain has a number in 1952 because the condition was false in 1952, but then 1957, it crosses that threshold, and then you have the rest of the data. So basically, this is an example of selecting data that satisfies a certain condition. And if we wanted to compute descriptive statistics on this, we could do the describe method. And this will compute the descriptive statistics ignoring the missing values. So for example, in 1952, the standard deviation is nan. And why is that true? Well, probably because there's only a single country, Kuwait, that had a GDP per capita that was greater than 10,000 in 1952. And so since there's only one observation, you can't compute the standard deviation doesn't exist when you only have a single observation. And that's why the mean, the min, and the quartiles and the max are all the same, because this is only a single observation. But then in 1957, you had two countries that satisfied that criteria. So now you can start computing actual statistics. And then it looks like by 2007, there were actually 13 countries in Asia that satisfied that criteria. Okay. Okay, so questions. So now would be a good time to take a short pause and just ask if there are any questions about this, about subsetting data, things like that. Okay, then in that case, we'll move right along. So the next thing that we're going to talk about is group by, split, apply, combine. So this is a fairly common paradigm for doing data analysis, where you take a data frame and you group it according to some criteria, and then you apply some kind of transformation to that data, and then you combine the data at the end. So the split, you split the data by groups, you apply some transformation, and then you combine the results at the end to get a new data frame. And these are all kind of techniques that you would do with your data before you would feed it into any kind of like machine learning or statistical kind of model. Okay. So for this, I actually do want to work with the Europe data. So I'm going to load the Europe data So that is read CSV, data, and was it Gapminder, GDP, Europe, CSV. And then we're going to use the index column, country. And I see a typo. Okay. Okay, so that looks good. So we've just loaded the same data set for Europe. Okay. So now what we want to do is we want to kind of give an example of this split, apply, combine approach. So the way I'll motivate this is we want to come up with a method to divide countries into countries that are relatively wealthy and countries that are relatively poor. And then we want to be able to compute some statistics based on whether or not a country falls, or based on the bins that these countries fall into. Yeah. So how might we do that? Well, one thing that we could do is to say, well, let's take a look at the average GDP per capita across countries. Okay, so this is the average GDP per capita in 1952 was over 5,000 US dollars, and in 2007 it was over 25,000 US dollars. Okay, on average. So what if we said, well, you are relatively wealthy if you are greater than, if your GDP per capita in your country in a particular year is greater than the average GDP per capita across all countries in that year. So that's kind of what this is saying. So like, if this is true, then the GDP per capita in a particular country in a particular year is greater than, for example, in 1952, it would be true if it was greater than this, or false if it was less than this. So if we look at this, then we can see we have this data frame that has all these trues or falses, depending on whether or not for that country in that year, its GDP per capita was greater than the average across countries in that year. So we've created, this is called a Boolean mask, and that's what we can use this mask to then subset the data. Okay. So we can call this, what should we call this? So I'll call this richer than average. Okay. So again, trying to use meaningful variable names. Okay. So what if we do richer than average? And what if we did the sum? What does this count? Okay. So this is counting the number of countries that were richer than average in a particular year. Because since we have trues and falses here, we can count the number of trues. So false would be mapped to 0 and true would be mapped to 1. And then we can count the number of trues by simply computing the sum, the column sum, so the sum across countries in 1952. So if we compute the sum, then that will give us, so 13, and then by the end that there were 17 countries that satisfied that. Now, if we wanted to do so trying to also follow the notes here. So there's another method that you could use if you want to do more more complicated transformations. So besides the sum, let's see what else we could do. So what if we did the mean? So if you did the mean, then this is giving us the number of countries who had a GDP per capita above the mean divided by the total number of countries. And if we wanted to compute the mean across not just the rows, but across the columns, so there is a, in the mean function, so here I've put my little cursor in between the parentheses, and if you do Shift and Tab, you can see the docstring for the mean method. So it has this axis, and the default value for the axis is across the rows, or 0. But if you change the axis to 1, it will compute the average across across the columns. And so here, instead of getting, so if we do axis equals 0, we get an average in a particular year averaging across all the countries. And so this gives us, again, the average number of countries that were richer than the average in a particular year. Whereas if we do this, we get the average number of times that the country was richer than average. So basically, if you look at a country like Austria, so Austria gets a score of 1. And that's because Austria had a GDP per capita that was higher than the European average for every year from 1952 to 2007. And then a country like Albania, which is a poor country by European standards, had a GDP per capita that was never higher than the average. And so it gets a score of 0. And then you have other countries that have about a third of the time, in the case of Greece, or half the time in the case of Italy. Your other countries that get scores of 1 are like the UK, Switzerland, Sweden, Norway. So these are all Germany, France. These are all wealthy countries. Okay. So what we have here is for each country, so for each of our row labels, we now have a score that we can use to group countries that have a common value for this score. So now we've created a numerical statistic that separates countries into different bins, where a country is in the same bin as the other countries if they have the same score, or if they have the same number here. And so we can call this the wealth score. And now we can use our, there's a group by method, which allows you to group the rows in your data set in a number of different ways. So you can group them by common values in a particular column of data, or you can pass in, as we're going to do, we're going to pass in a mapping between the row labels in our data set, the countries, and a value that determines what bin they should be in. So if we then do group by our wealth score, So this by itself returns a data type, a special kind of internal data type that's used by Pandas. But now the data, the rows have been grouped into bins depending on what value they got for this wealth score. And then you can do things like compute statistics for within the group. So here, if we do sum, then we get the total GDP per capita, which is a bit weird. So better to do the mean. So now we get the average GDP per capita. So this number here, 8,693, is the average GDP per capita in 1952 across only those countries who had a wealth score of 1 in 1952. And similarly, you can go through for the others. So this corresponds to this value of 6,436. So this is the average GDP per capita in 1962 for countries who had a wealth score of 1/3. So this is a somewhat contrived example, but I'm trying to demonstrate this concept of, you have a data set and you split the data set, the rows of your data set according to some criterion, in which case this is our wealth score. And then you apply a function and then combine the results. And the function that we're applying is the mean, and then Pandas handles the combine step and returns the data for us in one data frame. Okay, so there are some exercises now. I'm sure there's probably a lot of questions about the group by split, apply, combine idea. Feel free to ask them. There are some more involved exercises on kind of selecting and slicing and restructuring data. I will set aside probably 10 minutes to look at these exercises because they're more substantive than the ones that we had been looking at. Please ask questions. The questions, as long as they're generally like on topic, I'm happy to answer them. They don't necessarily have to be directly motivated by the lecture notes. But please take advantage of the resources that you have access to while we're doing this live training. So I'll set my timer for 10 minutes. Glinda and I will take any questions that you have. And if you have any questions about particular exercises, I can take a look at those as well for a group. I may pick one or two from this selection to go over as well if there aren't any particular questions. Okay, so let's take 10 minutes and get to work on these exercises. And I will stop sharing my screen. And then I'm happy to take any questions that anybody has. Okay, well, if there's no questions, while you guys are working on your exercises, I'm going to start putting together some, or thinking about which of these exercises I'm going to work through with this as a group. So there's a question in the chat about the descriptive statistics and whether or not they ignore missing values. And yes, they do. So this is one of the things that when you're doing data analysis versus when you're doing kind of like numerical computing, where when you're doing data analysis and you have missing data, typically you want to still compute your descriptive statistics and just ignore the missing values. Whereas in a lot of numerical code, you want to propagate missing values, because if the values are missing, it usually indicates that there's something wrong with the computation itself. And that is actually something where if you're doing a lot of NumPy stuff, you typically want to propagate not on numbers. Whereas with pandas, and where you're doing data analysis, you typically want to ignore them. And so that's what, by default, that's the setting in pandas, is that it will ignore missing values. Good question. Okay, so we're about halfway through the time I allotted for these exercises. How is everybody doing? Any questions? Maybe now would be a good time for me to just kind of work through one of the exercises. Or maybe I'll just wait and give you guys some more time. Okay, so I'm going to share my screen again, and I want to go through just some more practicing with selecting out data. So I'm going to go through this section here. So some practice with selection. Okay, so the first question is we want GDP per capita for all countries in 1982. So we can take Europe, and then we select using the loc method, and then we want to select all countries. So we can use the colon as a placeholder for all countries, so all rows, and then GDP per cap 1982. Okay, so that's the first one. So that's across countries in a particular year. What about Denmark for all years? So GDP per capita for Denmark for all years. So this would be Europe, a particular label, a particular row, so Denmark, and then all years. So GDP per capita for all countries for years after 1985, okay? So for that, we want all countries after 1985. So 1985, and then we can put a colon at the end to say that we want to select everything starting from that label up to the end. So we've got all the countries, and then 87, 92, 97, 2002, and 2007. So that looks right. I'll just put a little note here. So this was GDP per capita for all countries after 1985. For all countries and for all years after 1985. And then this next one is more complicated. So it's the GDP per capita for each country in 2007 as a multiple of GDP per capita for that country in 1952. Okay, so let's start with this as a multiple of GDP capita in 1952. Okay, so we've got our data, and then if we select for each country GDP per cap 2007, so that's the first half. So this is all the GDP per capita in 2007 as a multiple of GDP per capita in 1952. So to get the GDP per capita in 1952, it's the same thing, but just 1952. So let's list both of these. So here is 2007, and here is 1952. So to create a multiple then, what we would like to be able to do, what we want to do is we want to take Albania's GDP per capita in 2007 and then divide it by its GDP per capita in 1952, because then that will give us basically the factor by which Albania's GDP increased over the last 50 some odd years. And similarly for all the other countries. So we want to basically do we want to do division of this value by this value, where the division of the values are linked by the country. And so we would kind of hope that, given that both of these data series are indexed by the same index, that Pandas would automatically align indices and do the sensible thing. And in fact, that is what we get. And so what do these numbers represent? So what happens if your multiple is really big? What does that mean? Anybody want to put an answer into the chat?
Hey, David, there's a question there that probably you can best answer. I don't know if that one already got answered, though. About NANs and blank fields and
right. So, wait. So the question about about computing statistics with NANs. Yes, I did answer that one.
Yeah.
Okay. I did answer that one.
Okay, good.
So there's a question about the difference between using this kind of notation and using this this square bracket, or this kind of notation. And in some cases, it doesn't matter. So this is like a shorthand notation that works in a particular case when you want to select the column of a data frame. This notation works more generally because you are explicitly selecting which rows and columns you want. I generally prefer this notation because I think it's better to be explicit about which rows and columns of the data frame that you want, rather than this, which works for selecting a particular column. But if you tried to select for a particular row, this doesn't work. So to get the row, again, you have to use the loc notation. Okay, so I hope that answers the question. So back to the question that I had posed, which was this. So you look at a country like Ireland. Ireland has a pretty big multiple. So their GDP per capita in 2007 was almost 8 times higher than it was in 1952. So that's basically like, that's an enormous difference in your GDP per capita over a, just a little bit over a 50-year time period. And there's note that what would happen if one of these multiples was less than 1? What would that mean? So if it was less than 1, it would mean that the GDP per capita for that country in 1952 was actually higher than 2007. Yeah, so it would mean that the country had gotten significantly poorer. And fortunately, none of these countries in Europe got significantly poorer. We could do this calculation fairly quickly with Asia as well. And actually, before we do that, maybe we could even do, what was the best way to do this? Well, we'll just look at it just quickly. So if we did the same calculation for Asia, and let's look for countries that have, okay, so now you can start to see that there are countries, like most countries in Europe, the average multiple was pretty high. In fact, we could assign this, we could call this, I don't know, GDP per cap multiples for Europe. And I'll put in a few more. And then if we do, we could compute the average multiple for Europe. So what this means is that on average, a European country saw their GDP per capita grow by a factor of 4, almost 5, over the course of the 50 years in the last half of the previous century, more or less. And then if we wanted to do the same calculation for Asia, let me just get rid of some of these things. So first off, we notice that that there's a huge amount of disparity, right, in Asia. So just look at these numbers. So you've got countries like Afghanistan. So 1.25. So that basically they had a very modest increase in their GDP per capita over, you know, a 50, almost 60-year time frame. So a 25% increase, whereas, you know, on average, a European country got richer by a factor of almost 5. But similarly, you look at other countries like China. You know, Hong Kong is kind of more of a city-state, so that's a bit of a you know, its own thing. But China, you know, is over an order of magnitude wealthier than in 2007 than it was in 1952. I mean, that's just enormous. And then you look at Korea. So in Korea in the 1950s was a war zone, so that partially explains why its GDP per capita would have been so low in Korea. But so this is South Korea. And then this Korea Democratic Republic is North Korea. So South Korea is, you know, 22 times as wealthy now as it was 60 years ago. I mean, that's amazing. That's within a lifetime. I mean, some like 60 years, somebody could have been born, you know, before the war in Korea and have lived, you know, to the early 2000s and seen their living standards rise by, you know, a factor of 22 is fairly substantial. Then you've got Singapore and Taiwan. So there's an enormous range here. So maybe it makes sense then to look at, so we can call this multiples Asia. And rather than look at the mean, maybe we should just look at the descriptive statistics for everybody. Whoops, describe. And then we'll do the same thing for Asia. And so the mean, so on average, an Asian country had their GDP per capita grow by a factor of 6, which is higher than what we had in Europe. But if you look at the standard deviation, so the standard deviation, which is kind of a measure of like how variable were these, you know, GDP multiples in Europe, it's much lower than what you had in Asia. And that you could tell that straight away from when we looked at the data and we saw, you know, some countries had, you know, grown their GDP per capita by factors larger than 20. And then you had, you know, you had one country who had, whose GDP per capita fell over that course. And I think, let's see, who was that actually? Kuwait. I find that surprising, but I am a bit surprised that the GDP per capita in Kuwait would have been higher in the 1950s than in 2007, substantially higher actually, factor of 2 higher. So that's the kind of thing in a data set that would make me kind of pause and think, I need to investigate that a bit more and try to find out whether that there is some, you know, legitimate story going on about why that is the case, or whether there is, you know, issues with measurement, you know, incorrect data or something else going on. Okay. Excuse me. Okay, so questions about this before moving on. And kind of a, you know, interesting little aside there about some data analysis. Okay, all right, just going to move right along then. So plotting. So in this episode, we're going to do some basic visualization. You could do a whole course on visualization in Python. We're going to focus on matplotlib. It's the most widely used scientific plotting library in Python. But there are you know, a whole host of Python plotting libraries and packages and things that you can use. I would encourage you to reach out to myself or my colleagues at the Visualization Lab if you want to know more specifics or details or recommendations about plotting and visualization options available in Python. But if you're just making kind of static plots that you're going to drop into a paper or use in a presentation or something like that, Matplotlib is usually a good place to get started. Okay, so if we want to plot things, we need to actually load Matplotlib. So we are going to import Matplotlib. The particular module that we're going to import is something called PyPlot. Matplotlib itself is a huge library, has lots of different modules, and you generally only use some of the modules at any particular time, and so you import individual modules. And because we don't want to type matplotlib.pyplot all the time, we're going to use an alias, and we're going to alias that to PLT, kind of short for plot. Okay. So we're going to start by just making some simple plots, and then we're going to talk about how to plot, how Pandas has built-in support for plotting with different backends, including Matplotlib, for plotting our data. But if we wanted to just kind of create by hand a data set to plot, we could create some time positions like this, and or some timestamps and maybe some positions. Just make sure they're the same length. So we've got 5 times and 5 positions, and then we can do plot.plot time position. And then we can put a label, we can do plot.xLabel time y-label position. And we'll say, we can put our units in here, seconds or something like that. Right. And clearly I have a typo. So there we go. So we've created this little plot here, and we've labeled the axes, and so well, so good. So simple plotting. Now, if we want to plot data directly from a Pandas data frame, so that's kind of the next thing I want to show you. So let's load, just for purposes of, let's load the Oceania data. Since that only has two countries, it would be a little bit easier. It won't make such a cluttered plot. So we'll do read CSV data Gapminder Oceania GDP CSV, and our index column is the country. Oh, clearly I have mistyped the file name. Ah, yes. It's the other way around. There we go. And Oceania. Okay. So there's our data set that we want to plot. And what if we, well, let's just take a look. So there is actually a plot method for a data frame, and we can take a look at, it has a lot of options, so things that you can pass to customize the plot, tons of stuff. Well, so instead of reading too much in the documentation, why don't we actually just see what it does? oof, not really what we want. So what has this done? So this has plotted a line for each column. So if you call it without arguments, it plots a line for each column. So it's like plotted 2 data points, one for Australia, one for New Zealand for 1952, and then similarly for all the rest of the years. So that's kind of not what we want. We probably want to plot the GDP per capita for each country across time. So we want, so if we know by default it's going to plot one line for each column, then we could transpose the data so that the columns were labeled by country and then do plot. Well, there we go. So that looks a little better. Except now we've got these labels down here a bit garbled, written all on top of one another, and that's not so good. So maybe we could find a way to clean that up. And actually, in the teaching notes, there is some examples basically of how you could do that. And the way that you go about doing that is kind of by cleaning up. The issue is not so much, it's like the default labels are given by column on the x-axis. So it's basically just reading off what these labels are here and then putting them in the plot. So what we really want to do is actually clean up these column labels. And the way that we could do that, if we were so bothered, is that we could look at the columns attribute that we talked about earlier. So what we want to do is basically go through each of these values and strip out that and just leave the 1952. So if we were to do that, then we could, so that's what we want to do. So the question is, how do we get a hold of the string representations? So Pandas has a .stir attribute that allows you to get access to string methods that will operate on the series or the index that you're interested in. And then there's a string method called strip, which will strip out a substring, in this case GDP per cap and an underscore. And so now this gives us exactly what we want, except that we want, instead of the type object, since these are all years now, we probably should convert them to integers. So there's actually an asType method, which we can use to say we asType int, and then that gives us integers. And since this is a bit long and unwieldy, we're going to rename it years. And this is using accessing everything by .this, .that, .dot, you know, to access these different methods. We actually want to line these. This is called method chaining. So basically, instead of creating a bunch of intermediate variables, we can just continue to call dot some method to build up these transformations until we get a result that we actually want to store. And just to make things neat and tidy, you can actually line up the dots. And so this is how I would write this code in my own in my own work. So I would line all these dots up, and then I would replace the Oceania columns as the years. And now, if we were to look at Oceania, now we've replaced these kind of less useful column names with more useful column names. And now when we plot, it actually kind of gives us the nice clean column names that we probably wanted to begin with. So kind of one of the first things that you're going to do, whether you're doing data analysis with Python or any other language, is do a lot of data munging, data cleaning, data processing to clean your data so that it has nice row labels and nice column labels, so that later when you start actually doing data visualization and analysis, you can take advantage of the built-in functionality to more quickly get something that might be a production-ready plot or table or things like that without having to deal with special cases or something. So basically clean your data so that it's neat and tidy before you do any more sophisticated analysis. Okay. So there's lots of different kind of plot styles available. The default is, a line, but there is a kind argument that you can specify, and if you wanted to make it a bar chart, you could make it a bar chart, so it will give you something like this. You can set the style. So plot.style, maybe use. So there's a whole bunch of different styles that you can set. This documentation doesn't tell you a whole list of stylings. But there are many different styles. There's actually one that takes the ggplot styling from R and makes it available with matplotlib. So you get something that looks like, more like ggplot. I think there's another one called, is it XKCD? Well, there is a way to do XKCD style plots, which are like comic strip kind of plotting, which is kind of fun for presentations and things like that. But I can't remember how to do it at the moment. Okay. So we've been going now for about 2 hours. So it might be a good time to, I know we're in the middle of an episode, but rather than kind of rush through this episode and then take a break, why don't we just take a break now for about 10 minutes or so, and then we'll come back at 3, and then we'll kind of finish out the day with plotting, and then we'll move on to some for loops and conditionals and things like that. Okay, so I'm just going to save this. I'm going to stop sharing and pause recording, and then we'll pick up in about 10 minutes. Okay. Okay, so we're back from our break. So we're going to pick up kind of where we left off, which is about halfway through the plotting episode. We're just going to do some more things with plotting, and then we'll move on to some other for loops and conditional statements and things like that. All right, so I'm going to share my screen again. Okay, so here we were using the, basically the dot plot method for data frames to just kind of plot things directly. You can actually just extract the data from the data frame and plot it manually. So for example, if we wanted to say years is the Oceania columns, and then GDP is our data frame where we're going to select a particular country, Australia, and all the years, then we can use the plot method in matplotlib, and just like we plotted time versus position, we can plot years versus GDP. And then there's lots of ways that you can customize the different arguments and things like that you pass in. So if we wanted to plot a green dashed line, we can do something like this. You can have to read the matplotlib documentation. There's links to it in the lecture materials to really understand all of the different ways that you could customize your plot. most of the options that that you pass into this plot method of matplotlib are actually things that you could pass in to the plot method here on the data frame directly. And in fact, one of the recent areas of development and work in Pandas is to make this plot method sufficiently generic that it can plot, that it can basically be used to plot with different backends, not just matplotlib, but other Python visualization libraries that people would prefer to use instead of matplotlib. So there's a lot of innovation going on right now at this intersection of data analysis and data visualization in the Python community. So you could plot many things together if you wanted. So we could generate the same plot. Again, this is like manually going through and adding multiple lines to a plot. So we could go through here and add New Zealand, but now we need to differentiate. So I'll call this Oz and New, maybe NZ, AU. And then we can do GDP of AU, and then years GDP New Zealand, and maybe we make this one a blue solid line. So no, this is kind of getting something like what we got when we just called the this dot plot directly, except we don't have a legend and we've got different colors and things like that. So basically what I'm trying to get across here is that if you want to do something quickly, you can just use the pandas plot method, customize it a little bit. If you really wanted to do something like really bespoke and custom, then it's better to extract the data from the pandas data frame and then work with matplotlib directly or whatever visualization package you're using directly. So we could do more stuff, like we could add a legend and set the location of the legend to be in the top, or sorry, the upper left-hand side of the plot. So we didn't provide labels. So here we need to manually label the plot. Here we can, instead of using the default labels that you would get from pandas, you could put your own labels. And then of course we can add X label, year, Y label, GDP per capita, and title. Oceania GDP per capita, something like this. Trends. Something like this. And you can continue to customize and tweak the fonts and the font sizes and all kinds of stuff as you see fit. There's a call out box about more details about adding legends in the teaching notes. I'll leave that kind of as an exercise to the reader. So if we wanted to plot, so here we're plotting two time series, two countries' GDPs across time, but we could also plot their GDPs against one another. So we could plot the GDP of Australia against the GDP of New Zealand. And but instead of a plot, we probably want this to be a scatter plot. So there's like a simple scatter plot, and you can see that they're almost perfectly correlated. perfectly positively correlated, which makes sense. You know, these are GDP per capita for two countries that are geographically close to one another and geographically remote from other countries. So it makes sense that their kind of economies are highly related to one another. You can get, so instead of manually using the matplotlib API directly, you can actually get the same thing out of the data frame by calling plot, and then we can do scatter Australia and Y is New Zealand. And normally I would line these things up again like so. And so this actually returns, so this plot function call actually returns something called an axis subplot. And if you find that annoying, you just wish that it wasn't there, then you can actually just do something like this. And that will return this object and actually assign it to this variable underscore. And then you're not really going to use it. So it basically just makes it render a bit nicer in the notebook. Okay. So there are some interesting exercises in this plotting section that I would like you to take a look at. So if you want to take about maybe 10 minutes to have a look at these exercises. Some of them are related to doing a little bit of data analysis, and some of them are plotting. So I would encourage you to kind of go through some of them, and maybe we'll go through a few together. I guess just to wrap up, so there's a couple of kind of call-out boxes before I turn you loose on these exercises. So one is about how to save your plot to a file. Obviously very important. You know, if you're going to go through all the time to make a nice plot, you're going to want to save it so that you can put it in your paper or something. So there's a savefig function in matplotlib that you can call, and depending on what extension you put in here, matplotlib knows how to create basically PNGs and JPEGs and SVGs and pretty much whatever file format you want to save your plot in, and it will automatically determine what format to use by whatever extension you put in the name where you want to save it. And you can save it either into your current directory, or if you provide a path to the file where you want to save it, then you can save it in a completely different directory. And then there's some notes about ways to make your plots more accessible. Some things that people often don't think about is, you know, making your text large enough to read, making graph elements easy to see. So sometimes if your you know, your plot points are too small or your line widths are too small, it can be hard to see your plots. Also, a big one is colors. So a non-trivial amount of people have various degrees of color blindness, and depending on, you know, what kinds of color maps that you use, your plots may be completely indecipherable to somebody who has some degree of color blindness. So there's a couple of tools in here that you can actually use to check your own kind of color scheme to see how they would look to somebody who was colorblind, in case, kind of help you just be more aware of making better plots that will get your analysis across to more people. Okay. What else? So there is a nice link here to a graph, Python graph gallery for different tools for both matplotlib, Seaborn, and then Pandas together. And it provides you a whole bunch of examples of different kinds of plots that you can make with matplotlib, and then it will give you code examples for these as well, for how to do them. So one of the things that I typically do when I want to make a plot is I have some vision in my head of what that plot ought to look like, and then I'll come to a tool like Python Graph Gallery and just kind of look for a code example of something that is roughly like what I want to do, and then I'll just grab that code and then modify it as needed to work for me. Okay. Okay, so let's take about 10 minutes and have a look at these exercises, and then maybe we'll do a couple together, and then we'll move on. Okay, I'm going to set my timer and turn you loose. And I will start working through these exercises myself, I guess, and then unless somebody has questions.
Excuse me, I have a question.
Yes, Paul.
If we want to plot 3D data, how do we do that?
3D data.
Yeah.
Yeah. So there is So there is a module for plotting 3D data, and just looking for kind of the official documentation. Maybe take a look at this one. So here's kind of a simple example of a static kind of 3D surface plot. It kind of depends a lot on what you want to do, whether you want the data to be interactive or not, and what kind of data you're plotting. So if you have scientific data, there is a tool called Mayavi. Yeah. So if you're doing scientific visualization and plotting, there is a tool called Mayavi, which you can install and use to do the types of plots that you would typically get from scientific simulation data or things like this. If you're plotting like tabular 3D data doesn't generally come up nearly as much in plotting tabular data, but what kind of, did you have a particular use case in mind?
For example, if you want to visualize a seismic volume.
Seismic volume.
Mostly it's in 3D, yeah.
So okay, so I'm guessing that then seismic data would, something like Mayavi would probably be what you would be looking for, because if you're doing kind of 3D volumes and meshes and things, then I think something like this would probably be at least the place that I would start.
Actually, can I just interject something?
Yeah, Glendon might have, Python also might not be the best tool for that kind of visualization.
Actually, Python is good, but so what we use at KVL for scientific visualization is ParaView, which is actually VTK. It's a built-on VTK with a Python wrapper around VTK, the visualization toolkit, and that has so it has a large variety of visualization tools. Basically what you see in Mavi, but more, and it also is designed to handle very, very large data sets, and has the ability to basically be run on HPC systems and run distributed for very, very large data sets. We also give training on that. That will be coming around in the spring. If you go to the KVL training pages, and I'll put a link there, you can see some of the slides from previous years. You can also ask help at viz.kaus. I'll put that link in there as well if you have particular questions about using ParaView. But that's typically the scientific visualization tool. That's our go-to tool. And the good thing is related to this course is that using it, so basically there's a nice GUI interface to create your visualization pipelines, but underneath it is Python. It actually will auto-generate the Python as you use it if you want, and you will need that Python to, and maybe even to modify it a little bit, to create pipelines that run on the cluster. So your Python training here is still useful. I will go and put those links into the Zoom chat shortly.
All right, thank you very much.
Glendon, one thing that we to think about is we do have a mix of people who are within KAUST and not within KAUST. So anything on the training wiki, they may not be able to access directly.
So we don't have support for out-of-KAUST people at the moment from KVL, but there is lots of documentation online. Kitware, the company behind ParaView. ParaView, by the way, is open source and freely available. Also provides tutorials and lessons, and there's videos available on that. But at the moment, our focus has been on people using our systems like IBEX and Shaheen. Maybe
what we can do is when we post the video on YouTube, in the description of the video, I've been putting a lot of like important links or things that I talked about during the talk that I think would be useful references. So we can put a section on like visualization library links or something, and we can put a link to Kitware and ParaView and at least like the documentation or download and things like that. So you can at least get take a look at what's required and maybe find, if you're not here at KAUST, then maybe you can find some more local help to wherever you are on those tools. Cool, yeah. Okay.
Yeah, that's okay. Thank you.
You're most welcome.
Yeah.
All right, so there's a few minutes left on my timer for the exercises. So I'm just going to start kind of going through some of these exercises myself to, and then maybe we can talk about them. Actually, I think rather than just, it would probably be better for me to annotate and talk about my solutions as I go through them. So I'll just give you guys a couple more minutes to keep working, and then I'll just walk through them and kind of talk through my solutions as I go. So let's just go through some of these. So the first exercise is minima and maxima. So, and it's giving you kind of mostly some complete code and just wants you to kind of fill in the blanks in order to get it to work properly. So we already have our European data loaded. So we can compute the min of the data, which is going to plot the minimum GDP per capita across all the countries in a particular year. So this would give us a time series, and we can plot that time series. So this is plotting the minimum, and we probably want to give it a label. And we probably want to clean up this, this bit. So if we do, remember we have our years, and so the years are the same for all of the countries, so, or for all of the data sets, so we can just reuse them. So we could do the Europe columns years. So that cleans that up. And then I would what would I do? So then I would align all these things. And then add a legend. And okay, so we added a legend. And if we wanted, we could rotate these, just as an example of how if you wanted to rotate the ticks on the x-axis, you could look at the x ticks attribute, and then you could say rotation is 90, so 90 degrees. And so that tilts them so that they're facing down. And again, we can suppress this kind of madness by just doing that. But maybe 90 is a bit much. So if we did 45, that looks kind of a bit nicer. So leave it like that. And excuse me. If we wanted to plot the max, then what could we do? Well, we could basically just do the same thing again. You could just change this to be max. And then, of course, we need to give it a different label. So there we go. So that's plotting the min and the max of GDP per capita in Europe. Some examples of label rotation, things like that. Okay. So the next one was on correlations. And so we want to plot, scatter plot showing the relationship between the minimum and maximum GDP per capita countries in Asia for each year in the data set. So is there any relationship? So we have Asia data, should be already loaded. Yeah. So for each year in the data set, so we can compute the descriptive statistics. Describe. And this descriptive statistics is itself a data frame. So we could actually, again, we could select certain things of this data frame by row labels, so like count, mean, standard deviation, blah, 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 or columns. So we could do, like if we wanted to select the mean, we could just do the mean for all years, and that would give us the mean, just as an example. But if we were to call the plot method, so this is, again, plotting a line for every column, and then the things that it plots here, I mean, this is kind of like a nonsensical plot. Like, it doesn't make any sense to do this. But if we transpose the data, then that's plotting the time series of these different things, counts, means, quartiles, min and maxes across time. Then we could also I'm gonna just clean this up a little bit. We could do kind equals scatter. And then we could say the x that we want to plot is the min. So we want to scatter plot the min against the max and see if there are any obvious patterns. Y. So no obvious patterns there really. So one thing, right? Okay. So basically, I'll just stop there. So that's an example of how you could get a nice elegant way to do a scatter plot of kind of aggregate statistics by plotting the output of the describe function, which is itself a data frame, which has a plot method. Okay. The next example is about kind of helping you go through the documentation and kind of figure out what all of this does. So first, we're going to load a new data set, which is the data all. So we're going to do the read CSV data gapminder GDP all, or no, gapminder all. And let's just look at this data because we've not, dot CSV. And then we can look at this data, just the head, to kind of see what it does, or see what it looks like. So we have an example of maybe a multi-index. And so we've got continent and then country. So we might want to index on 2 columns. So we can do index column, and now we can put a list. So we could put country, and then content. Okay. And so now we have this index data set. And now what we want to do is we want to plot. So again, if we do just a plot, we're going to get a plot for each column. So it's going to plot a whole bunch of stuff. Now we've got GDP per capita, we've got population, we've got a lot more things, a lot more columns. In fact, let's look at the columns that we have. So you've got GDP per capita, life expectancy, and population for all of these different years. So we've got a lot more data to plot. So if we just call the plot method, we get a nonsensical plot. Like there's just tons of stuff plotted here for country continent pairs. Like it's a bit of a mess. So what do we want to do? Well, we're asked to plot a scatter plot between GDP and life expectancy for 2007. So we want to do a scatter plot. So if we do kind is scatter, and then we want to do GDP per capita in 2007, and this is our X variable, and then our Y variable is life expectancy in 2007. So let's see what that does. Right. So this is giving us a scatter plot of selecting out two particular columns from this big data set, this larger data set, GDP per capita and life expectancy. And the idea is that as GDP per capita goes up, you would think life expectancy should go up as well. That richer countries should have higher life expectancy. And that does seem to be the case, but it seems like it's a highly nonlinear relationship, that actually life expectancy goes up really fast as your country, if you're poor and you become even a little higher GDP per capita, then your life expectancy can go up quite a lot. Whereas once you reach a certain level of GDP per capita, actually increasing GDP per capita doesn't really increase your life expectancy that much. So it's a very nonlinear kind of relation. So there's other things that we can do. So each of these points is an individual country. Now, countries that have different populations. So like China has a really big population. A country like, maybe Singapore has a very small population. So maybe if we made these, we could see something interesting if we made these, the size of the scatter plot, or the size of the point in the scatter, proportional to the amount of population that you have. And so one way we can do that is by setting this S parameter, which controls the size of the scatter plot. And so we can just say that the size of the scatter should be what is it that we wanted it to select out? So we want to use the population in 2007. But instead of using number of people, we want to use millions of people. So we'll divide by 1e to the 6th, which is 1 million. So now this is all getting very kind of hard to read. So I'm going to go ahead and just kind of stack these arguments in here just to make it a little bit easier to read. And then I will suppress the output. There we go. And we could do even more. We could go in here, we could color the points by continent. And if we wanted to. So this big country here is probably China. We could add like labels and things like that. But I don't want to go, you could kind of, any of you who have created plots for papers and things like that, you know that there's kind of you can almost spend an infinite amount of time, tweaking these plots to, depending on what you wanted to do. What else? Is there anything simple? I think there should be a log y. That's what I wanted to do. So this, or log x rather. So we could maybe try to do a transformation of the x-axis to make this a little bit more linear. So if I do log x is true, and so what I did was I put my cursor here and I did Shift Tab, and then I started glancing through here for something that might map to changing the scale of the x or y axis, and there's this log x, which you can set as true or false to logarithmically scale either the x or y axis. So if you set log x equals true, that's going to rescale this logarithmically, which is going to have the effect of making this probably a little bit more linear, because you're going to spread out the points that are in this region relative to the points that are in this region. Yeah, so there we go. So that makes it kind of quite a bit more linear. And the reasoning here is that GDP per capita ranges over several order of magnitudes, and life expectancy only has a very narrow range, right, between 40 and 80, versus GDP per capita ranges between, so 10 to the 3, so this is 1,000 and almost, so down here on this end you have, you know, maybe 200, and then on this upper end you have 100,000, so that's a big, or nearly 100,000, so that's a big range, basically. Okay. Right. So questions about plotting before we move on? So now would be a good time if you have like particular kinds of plots that you're interested in doing. Obviously, I can't give you like necessarily a live demo of the type of plot you're looking for, but you know, I can make notes about plotting libraries that would solve that problem, and then, you know, pass links around either now or in the YouTube video description. So like the peer review links, we'll be sure to put links to peer review there because there's a question asked about that. Okay, well, I'm going to move right along then. Okay. I will. Okay, I will share my screen again. Okay, so the next topic we're going to cover, so now we're going to shift gears away from data analysis and visualization and kind of go back to standard Python, or kind of standard library Python, and talk about some kind of common data structures that you encounter when working in Python, and then some common patterns of for loops and conditionals and things like that. So we're going to start with lists. So a list is basically a container where you can store multiple values instead of a variable that stores a single value, which is kind of what we've worked with so far. You can have a list can store multiple values. We'll talk about use cases for collection of values and different ways to modify lists and things. So switch back over to Jupyter Lab. So lists. Okay. Okay, so a list, you can store many values in a single container. So, you know, we can define a variable pressures. And I've done this a couple of times already, but now we're going to actually talk about lists. So you can have, you know, some floating point numbers. I'm just kind of putting numbers in here. Okay, so you could have some pressures. And then if you were to print pressures, you would get something that looks like this. Again, it just prints kind of a string representation separated by space. You know, just like a string, you know, something like a list has a length. So you can compute the number of items in a list. You can index into a list just like a string. So you can get the first element in a list. You can get the last element in a list using negative indexing. Unlike a string, where a string was immutable, you couldn't change a string. You can change a value in a list by assigning to them. So if I want to change the last item in a list and make it to be, you know, some really large number, then I can just assign. I can use the index to basically grab a reference to the last value in the list and then assign it a different value. And so now I've changed the last item in the list. A list is a data structure that you can append things to. So if I append an item to a list, so for example, if I created a list of prime numbers, 2, 3, 5, 7, then if I append the next item to the list, notice that this doesn't return, it returns everything returns a value, but the value that it returns is none. But now if we look at primes, it's appended that value to the list. There are lots of list methods. There's another one called extend, where you can extend a list with another list. So if I said the next primes were what, 13, 17, 19, 23, and then you look at primes. So now we have a list that has been like concatenated a list together with another list. Now, if I did primes.append and then I passed in another list, and that was the next set of primes. So, gosh, now I'm running up my ability to just generate prime numbers on the fly. So maybe 29. Some other ones. 31. Notice what's happened. So I've appended a list as the last item in a list of what was previously just a list of numbers. So the thing to note about a list is that a list is a container that can contain, it does not have to have the same data type for each element. And it can have, can hold different types of things. So here we have a list of integers, and then the last element is itself a list of integers. So there is an empty list. You can create an empty list. So this is just a list that contains no elements. It's like the zero of lists in some sense. And this is useful because if you want to use a list as a data structure to kind of collect values and store them in a list, then you're generally going to want to start with an empty list. And then you're going to do some processing and then add an element to a list and append another element and append another element, and so on and so on. We're going to see some patterns like that in the next episode when we start processing data files. So I already mentioned in the lecture notes that lists can have different types. Values stored in lists can have different types. And I guess we talked about indexing into strings, but I guess I didn't mention that strings are immutable. So if you have a string like this, so you can index, but you can't do something like this. So unlike lists, where I could assign the 0th element in a list to be something different, change its value, I can't do that with a string. Strings are what is called immutable data type. It means it can't be changed. Indexing beyond the end of a list will give you an error. So we've got our primes, and then the length of primes. So if we try to select this element, we'd get an error, a list index out of range error, because remember, indexing starts at 0. and the length of primes will be 1 greater than is needed. So if we subtract 1, then we can select the last element in the primes, which of course was this kind of goofy list that we put in there. Okay, so let's go back here. The rest of this episode is some exercises. So I want to give you a few minutes to go through these exercises. And then, so I'm just going to cover the key points, and then I'll turn you loose on the exercises for a few minutes before we move on. So a list stores many values in a single structure. You can index into lists to select individual values. You can replace the values in a list by assigning directly to them. You can append elements and extend lists, append elements to a list and extend them. You can remove items from a list. There's an empty list, which we're going to see is a useful starting point for accumulating results. And then, unlike lists, strings are immutable, so you cannot assign values to a string, an individual character in a string. Right. Okay. So why don't you take maybe five minutes or so, and just have a work through some of these exercises. Play around a little bit with lists and see how you get on. I'm going to set my timer. And let me know if you have any questions. So it looks like there's been some discussion about seeing local variables. And a Jupyter Lab variable inspector. This is something that I was unaware of. Well, thank you, Glendon, for digging that Jupyter Lab plugin out. I will have a look at that and perhaps add it to my notebook for next time, or the environment for next time. It looks useful. And let me just see what version of Jupyter Lab 1. It might be a problem. Okay. There's also some Ipython magic commands for doing this. I don't often use them, and so I can't remember them off the top of my head. There's one called whos, and this has everything that is defined. So there is an Ipython magic command called who and then whos that shows you some information about variables. And it's a bit kind of cluttered to the point of being perhaps not so useful. Like that, yeah, that's almost useless. So this is a little bit more useful in that it gives you the variable and then the type, and then some information about the data itself, so like a shorthand representation of the data, and whatnot. So I'll leave this here. So useful Ipython magic command, and let me pull out a built-in list. So I'll put this here. So this lists some of the information, but I'll have to take a look at what Glendon linked in the chat, because this variable inspector looks quite nice. It looks more like something that you would see in RStudio, which has a really nice kind of variable inspector GUI that allows you to kind of see what's defined. So I'll see what I can do for next time on that regard. Okay, so there's our 5 minutes gone. So let me just take a look here and see. Well, I guess first, were there any particular exercises that you want me to go through as a group? Otherwise, I might just pick one somewhat randomly. Okay, well, then I am going to do sort and sorted. Okay, so we have two programs. So we've got program A, whoops, which takes some letters, which it gets from using a function, a built-in function called list, which takes a string and converts it into a list of characters, like this. So we'll call those letters. And then the result, sorted letter, uses another built-in function called sorted to sort the collection of letters. And then we're going to print the letters is letters and result is result. Okay, so here we are printing the variable letters, and so it's just, you know, GOLD, like we would expect. And then result is letters, but then sorted alphabetically. So they're two different things. So letters and result is different. So for program B, we're going to make a small change. We're going to, instead of using the sorted function, we're going to use the sort method on letters, on the list letters. And here we get something completely different. We get what in the first program we got as the result is now what we get as letters, and with result we now have none. And what's going on here is the sorted returns a new list. So the sorted function, if you were to go and look at its documentation, it says it returns a new list containing all items from the iterable, and there are many kinds of iterables. The list is just one in ascending order. So that's why it does not modify the existing list, it just returns a completely new list. So that's why we get two different, the letters is the original list, and then result is a completely new list that's been sorted. Whereas sort actually sorts the list in place. So the list itself is modified. And that's why, because the list is modified, the return is actually none. So if we were to look at the type of result, it's the none type. And that's why letters is sorted in place. So the original data structure here, which is a list, G-O-L-D, is then moved, the values in the list are moved around in place. So the difference between when you have a data type that is mutable, that you can change the components of that data type, you always have to be careful about whether you're modifying it in place or whether you're creating a completely new list. Depending on how large your list is, sorting and generating a new list when you only have 5 elements, the difference between these two is, in terms of performance, is negligible. But if you had a list that was like 50 million elements long, then there might be a big difference in terms of the performance of the sorted function that returns a new list and the sorted method which modifies in place, at least in terms of memory usage. Okay, so I'll leave the other exercises. The solutions are all there, since no one has any particular questions about them, and we'll just move on to the next episode. Okay, for loops. So for loops are probably one of the most useful kind of programming constructs for automating repetitive tasks and automating research processes and things like that. So it's a technique for using it's a programming technique for doing the same thing over and over again on different inputs. Is the basic idea. So we're going to kind of trace the execution of a simple loop and then see how the variables change as each iteration of the loop goes. And then we're going to show how to use for loops, something called the Accumulator Pattern, to aggregate values. So it's a kind of a common pattern that's used quite frequently for for loops, or quite frequently with for loops. So do for loops. Okay. So let's see the simple syntax for loop, and then we'll talk about the different components. So for a number in 1, 2, 4, 8, 16, print the number. Okay. So what I've called number here is the loop variable. So this is the variable whose value changes at each iteration through the for loop. Then this collection here is the values that you want to pass into the for loop at each time. So here, these are simple numbers, but they could be arbitrary things. It could be data sets, could be CSV files, it could be Pandas data frames, it could be Python objects that represent matplotlib visualizations that you want to do some kind of processing on. Could be raw JPEGs that you want to process before you're going to feed them into something else. Could be anything. You could be doing a for loop of, if you're doing a machine learning hyperparameter optimization in some crude way, you could have a model pipeline that you estimate, and then you're going to loop over different configurations of parameters and then retrain a model each time and accumulate the resulting trained models to try to find the best model, something like this. So this type of for loop pattern comes up quite a lot. Okay. So, and I talked about, so just syntactically, so the first line of a for loop must end in a colon, and then you have 2 keywords. You start with for, and then the loop variable, and then you have the in keyword followed by the collection of variables whose value will be passed into the loop variable, and then a colon. And then some indentation followed by the body of the for loop. So anything that is indented underneath this first line of the for loop constitutes the body of the for loop. And then when the for loop is done, you kind of remove the indentation, and now this executes after for loop terminates. So that, notice this executes once after the for loop terminates, whereas if I put another print statement in here and indented it, this executes each loop iteration. So here the indentation matters. Okay. And if you don't provide any indentation, then you're going to get a syntax error. And that's generally true. Indentation is meaningful in Python. So the example in the notes was that if you did something like first name Jane, last name Doe, you'll get an indentation error. Because since indentation is meaningful, when Python encounters some indentation, it somehow thinks that, oh, well, this ought to be like a for loop or a conditional or some kind of statement like that, and it's not. So it just fails with an unexpected indent. Error. Okay. So again, so there's nothing. Loop variables can be anything that you want them to be. So you could call this, kitten, and the result is the same, but this is kind of nonsensical, right? So meaningful variable names are important, and that applies to loop variables as well. So if you're looping over file paths, you could do for file path and file paths. Or if you're processing, a collection of models, you could say for model and models, and you could define the list of models somewhere else. So you'll use this kind of pattern, and we'll see some examples of that. Loops can have arbitrary, things going on. You can, have a whole bunch of statements in here, kind of whatever you want to do. The body could be one line or it could be 1,000 lines. It just depends on what you're doing with the for loop. There's some built-in functions for common patterns. So instead of, you can do for number in a range from 0 up to but not including 10, print the number. So this is a useful built-in function for computing like just a range of integers over which to iterate. It has some nice fancy, it's technically something called a generator. So, if you were using this pattern and instead of 10, you were looping over, what is this, a billion, a for loop that was kind of go through a billion different things, then this range would not create a list of a billion integers, which would use a lot of memory. It will instead just feed one integer at a time into number without blowing up the memory usage. So there's other little, little micro optimizations and things like that in Python. Right, so let's look at the accumulator pattern, and then we'll see some actual more real-world use cases in the next episode. So we define kind of a 0 for our accumulator pattern. So if we're going to compute a sum, we might start with the total that is 0. And then for number in range of 1,000, total plus number. And maybe we want to go to the first 10 integers starting at 1 and going up to and including 10. So we'll go to 11. Then we could do something like this. And then if we look at the total, and then I think that there's an old formula for this kind of a total where it actually would be 10 plus, or 10 times 11 divided by 2, I think. So if we set, instead of making this 10, we can make it arbitrary. We could say we want to sum the first in elements, and let's make in 100. And then we can replace this with n. And then if we run the loop, we get this answer. And this, I think, is n times n plus 1 over 2. Yeah. So then we can make this really big. We could make this like, what is that? So that's 1,000,000. Or 100 million. And I suppose that this would be an example of when it's better to be clever than just using brute force computation, right? Because this for loop is going to come to the same result of accumulation, taking on the order of seconds, whereas this formula is obviously going to give you the correct answer instantaneously. And this might be a good time. So there is another magic command, cell magic command called time it, where you can actually time the how long it takes to do the calculation in this cell. And it runs like a little, depending on how long the computation takes, it'll run like a little experiment and maybe run the command several times and then give you kind of an average, how long it takes on average and what the standard deviation was for the runs and things like that. So that's another handy little trick. And hopefully this won't take too much longer. I can't remember how many it runs by default. I think it runs like, I think 3 or something if the first computation takes too long. Okay, so let's see what else is while we're waiting on that. So there are some exercises. Okay, so here we go. So it did, it ran this computation 7 times, and it did for 1 loop each. So basically it would normally run a certain number of times, and then for each time it would run a little for loop and run the same command over and over and over again. So it did this 7 times, and basically it took about 6.7 seconds, plus or minus 190 milliseconds per loop. And now this formula, of course, is going to be much faster. So that actually took 257 nanoseconds. So, a nice example both of how to use the timeit command, but also the benefit of being clever in your algorithm choice, shall we say, for arriving at a particular result. Okay. The rest of this episode is, again, more exercises. So there are several opportunities to practice this accumulator pattern. And so why don't you take a look at those? So just to be clear which exercises I'm talking about. So at the bottom here of the for loops episode, there are several exercises for accumulation practice. So I would encourage you to take a look at a couple of these. So I'll set the timer for 5 minutes and then we'll move on. And I will be right back. Okay, I'm back. So any questions while you guys are working on those exercises? No? Okay. I will share my screen again, and then I will just take a look at some of these exercises myself, maybe pick one to walk through in a minute. Okay. So I'm just going to go through a few more examples of the accumulator pattern. So the first one was the total length of strings in a list. So we start with this, the data that we would start with would be this list of strings, and we want to compute the total length of all the strings in the list. So oftentimes the trick to getting the accumulator pattern working is to spot the correct choice for the starting value. So here, we're adding things. So 0 is the 0 element when you're talking about adding things together. So setting total to be 0 is the right choice. And then this is this is a short notation for this. So these, so for total plus equals length of the word. And so that will give you 12. If you want to compute the list of word lengths, if that's the output that you want, then the 0 element that you start with is the empty list. Move this around. So we start with our data, and then we start with the empty list, and then we just append the results to the empty list, and eventually we build up a list of word lengths, which is what we want. And then there was another example, which was concatenate all the words. So here, we want to start with the empty string. And then once we have our empty string, then we can do string concatenation. With the plus. And then the final one was create an acronym. So we have words and we want to create an acronym. So our result, again, will be the empty string, but instead of the whole word, we want to select the 0th element, but then we want to make it uppercase. So I think there is a string element called upper. Yeah, upper. Okay, so just those are some more examples of an accumulator pattern. And the takeaway is that the trick to apply the accumulator pattern is, again, what is the 0 element? What is the best kind of value to start the accumulation from? Is it an empty list? Is it an empty string? Is it 0? And then note that inside you're doing some kind of binary operation. In this case, it's something that is kind of like addition. Alternatively, if we wanted just as another example to get you thinking, so if we wanted the product of lengths of strings, then the total, the element to start with for the total would not be 0, but rather would be 1. Because 1 is the thing that if you multiply an item by 1, you get the item back again. So here, maybe this would be better to name this the result. And then result, we could do times the length of the word. Just as another example. And so that is 3 times 5 times 4. Okay, cool. Any questions about this accumulator pattern before we move on? Okay, doesn't look like it. Okay, so we will move on. Okay, so now we're getting down to close to the end of time. So we've got conditionals and looping over data sets. So what I want to do is, I think for now I want to skip conditionals and do looping over data sets, because I think it follows nicely from the for loops and the accumulator pattern, and it's a real world use case that I think you might find instructive. So there's some basic syntax issues that are covered here for conditionals and how they work and how they can work inside of loops. So I'm going to just skip over this and leave this as an extra, as a lesson for you guys to go through on your own. And instead, we're going to take a look at looping over data sets, and then probably we'll have Q&A, general Q&A, if there's any interest. Right, so looping over data sets. So we're going to talk about how to process many data sets with a single command. So this is a common workflow issue that you might encounter in your work here at KAUST, or in your own work wherever you are. So let's talk about how to do this. So okay, looping over data sets. Okay. So basically what we want to do is we're going to have a list of data sets, and we're going to use the for loop to process each data set in the list and do the same thing over and over again. So the first thing we want to do is write out just our kind of stub loop. So for file name in file names, we're going to have data and read CSV from the file name, and then let's just leave it at that. And then we'll do print data.head. Okay, so if we were to execute this, of course, we've not defined file names, but we've kind of more or less sketched out our loop and what we want to do. And this is often how I write my own for loops, is I will write it like this and run it so that it fails, because sometimes actually getting this is the most difficult part sometimes. And we're going to see how to do that in just a minute. But conceptually, we want to loop over a file name and a collection of file names. We want to read the CSV file, and then we're just going to print out the first 5 lines. So then file names, where does this come from? Well, we could we'll start by just manually entering our list of file names. So we know that they're all in the data directory, and they all have a particular form. Asia. So they all kind of look like this. So now let's try this. Okay, so there we go. So this basically, we looped over 2 data sets and just printed the first 5 lines for Europe and then the first 5 lines for Asia. Okay, so that didn't do anything, you know, hugely difficult, but it's just a simple loop to kind of get us going. So then the question is, well, what if this data directory contained, you know, 1 million files or something like that, which, you know, and some of my colleagues in the KAUST supercomputing lab that do genomics and bioinformatics, they typically have many tens of thousands or hundreds of thousands or more of files, and they need to process these files in the same manner repetitively. So we don't want to have to manually write out the file names. So how can we improve upon this? And the answer is to use a package called glob.
Excuse me, can I just ask a question?
Yes.
Thank you. In the for loop, I didn't see where you specify the first 5 rows or whatever to be printed. Can you just explain in the for loop? Yeah.
Yes. So that is the default value for the head command. So here's the 5 right there. So basically, if I set n equal to be 10, then this will print out the first 10 rows, but the default value is 5.
All right. Good.
Okay.
Yeah. Thank you.
Okay. You're welcome. So we're going to use this glob to get a list of file names. And glob has a function called glob. And if we look at the documentation, it uses a technique called pattern matching to match, to grab a list of files from a path that match a certain pattern. For example, our file names all start with data and then gapminder GDP, and then they all end in some number of characters that represent the continent, roughly, and then they all end in CSV. So they kind of all fit this pattern. So what this will do, and I'll just copy this out, is it will go and grab all the files that match that pattern and return them in a list of strings, which is exactly what we want. So now, whether this directory had 5 CSV files or 5 million CSV files, this for loop would process each of those files one after the other. Okay. Now, typically, this isn't, we're not just going to print out the first 5 rows. We're going to do something more, more substantive. Like we could do, descriptive statistics. So here we could print out all the descriptive statistics. And if we wanted to do that, we could then, from the descriptive statistics, we could also then select out the mean from the descriptive statistics. So here we're getting a time series for the values of the mean for the different files. So we could then even do something like this. We could keep going along these lines, and we could do a plot. And so now we've created a plot of the average GDP per capita for the different countries. We could do, we could add a label. So how do we get a label? Well, really the only thing we have for a label at the moment is the file name. So we can stick that on there. And then we need to add a legend. Yeah, and that legend is a bit ugly. It would be great if we could just kind of carve out this Oceania. So how might we carve out Oceania? Well, these file names are strings, right? And we talked about a strip function earlier. So if we wanted to create a label for our plot, we could do file name. And what I'm demonstrating here is how kind of I would interactively tweak a result to get something that I wanted. So I started with a simple loop, and I've continued to kind of add complexity to get a result that I'm happy with. So this file name is going to be a string. So if we strip out the part of the string that we don't want, GDP underscore, and let's see what this does. That didn't work as expected because I now need to change label. All right, so that's a little bit better. But then we want to, no, that didn't quite work, did it? Why did that not work as expected? Well, when in doubt, troubleshoot by printing. Oh, it's not, it's stripping out, I see. So this is not then the right method to be, to use, because it's stripping out all of the characters that are included in this list of characters. So that's why it's stripping out the A's, any A, any G, any P, any M, and so that's why, so that's not at all what we want. So we want something, something else. Well, we could do it by string indexing. That might be a bit tedious. So let's try it anyway. So we want to strip out everything starting from maybe the 10th character to the end. Let's see what this does. All right, so let's try the 20th character to the end. Almost there. So 22, right? And then to minus, oh, almost there. So there we go. So that uses some fancy string indexing that we talked about earlier to kind of strip out the label and then plot, the average GDP per capita. And note, if we wanted to clean up this mess down here again, we could set the data.columns to be equal to the years variable that we defined up above, because it's the same for all of these. Isn't it? No. Apparently it is not. So then we won't do that. That's good enough. Okay. So we saw some examples of looping over data sets and making a plot. what I often do in some of my machine learning workloads is that when I'm looping over data sets, I'll often have a step in here which will be so this will be a common ML so with for loops. So I will glob.glob my CSV files, and then I will loop over my files, and then I will load the files, and I'll have some step which will be like pre-processing data, and that will create some processed data, and then I might have a model fit on the processed data, and then I might accumulate some fitted models in a list, and so I might have fitted models, something like this, and then up here I will have a model, and that will be some model that I will have created, and then some function for processing the data and store the models. So this is an example of how you might apply the accumulator pattern in some kind of a machine learning workflow or a statistical modeling workflow where you're applying the same modeling process to each of a number of data files, something like this. Okay. So questions about this idea of looping over data sets?
Excuse me, I have a question.
Yes.
How about the situation whereby we need to use double for loops?
Okay, so that's called a nested. Sure. So that's called a nested for loop. So a nested for loop, just from a syntax point of view. So I'll write this kind of like a MATLAB kind of for loop you would see. So for I in range 10, for j in range 10, print I times j. So this would be an example of a nested for loop, just of the syntax. So you have, and note the indentation. So you've got the outer for loop, followed by the inner for loop, followed by now the body. And so this body will be executed for each combination of I and j. But of course, you could have statements here that only execute, that this statement will execute executes for each would execute before the inner for loop. And then once the inner for loop is done, you could have another statement in here, which obviously would executes after the inner for loop. And so for each value of I, both these statements will execute, but then because of the indentation, you can see that this is going to execute, or or you see how the indentation lines up. So for the outer for loop, each iteration of the outer for loop executes this block of code. And then the next level of indentation, this only gets executed for each combination of I and j. So that's just kind of like the rough syntax of a nested for loop. And you can continue this if you wanted like triple nested for loops or something like that. Depending on what you're doing, if you're doing numerical calculations, then nested for loops are to be avoided in Python because they're quite slow, and usually you can use things in NumPy or other packages to speed up those kind of computations quite a lot. Does that answer your question, Paul?
Yeah, I'm okay. Thank you.
You're welcome. Change these to be smaller numbers. Okay. This would be a good practice if you understand the execution about why this nested for loop prints out these results in that order, then you really understand for loops in Python. Okay, so we've got about 15 minutes left. So I think rather than try to rush through another episode, I'd like to allow you some just Q&A time. I think is probably the best thing to do. And then, of course, these course materials they're always online. They're not going away. I update them from time to time. But you can go through the rest of the episodes that we didn't cover on your own. And you can ask questions, either reach out to us, Glenn or myself, and ask us questions when this is done. Our YouTube channel is very new. You can always leave comments on the YouTube channel, and perhaps we'll monitor and answer questions that we see there. But we're all kind of just stepping out into delivering our training in this virtual format and kind of sharing it via social media. So we'll have to see how that goes. Right, so any questions about anything that we've covered today? I know it's been a long day, and we've covered quite a lot. So I expect everybody is quite tired. But if you have questions, then now would be the time to ask.
Do you know any app or anything that's meant to make us exercise, provide more exercises for us to code, because we might not need it every day, and like data camp for R, for example, something similar. So
right, for places to practice. So that's a good question. So I will have to think about that. I mean, yeah, the short answer is that there are many. I just can't think of kind of my top 3 best ones to include. But I will be sure to add some links to kind of places to practice and learn more. If you're interested in, I guess the only thing I would say is that if you're interested in data analysis or machine learning, there are 2 books that I would highly recommend. And I will be sure to put links to these. Okay, I knew that there was a GitHub repo. And Amazon and so one is, so this is Wes McKinney's book on Pandas. So this is kind of like the canonical reference material for Pandas. It includes a whole bunch of notebooks that you can use with all the code and everything in there, that you can go through and learn kind of quite a lot more about the details of pandas and how it works. And then similarly, for machine learning, there's a great book called Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow. And it covers you know, a little bit of pandas, but mostly on how to do machine learning in Scikit-Learn, Keras, and TensorFlow. I highly recommend these two resources. I've been through both of these books kind of cover to cover, and that was how I got started, or that was how I really got my hands dirty in getting to know how to do this stuff, was with the first version of both of these books, and now they subsequently come out with 2 new versions, and updated them and everything like that using the latest libraries and tools. So I would recommend both of those as starting points to learn more.
Yeah, thanks a lot.
And I'll share these in the chat now, just so I don't forget. So so the reference book for pandas and a reference book for machine learning. And both of these books, digital versions of these books are available through the KAUST library. So, I mean, obviously you can buy your own hard copy if you wanted to have your own personal copy on your desk, but there's digital PDF versions that are available through the KAUST University Library. So you can just go onto like library.kaust.edu.sa and then put in the title of this book, and you should be able to find it without too much trouble. Okay, any other questions? And actually, now that I think about it, I ought to put these links here, since I'm going to put, so this notebook from today, I'm going to save, and then I will put it on the GitHub repo. So if you want to come back and look at this and see all the stuff that I typed and any links that I typed and things like that, then you will have this as a reference.
Your video will also be available there?
I'm sorry, say that again?
The video of today will also be available
the video
there.
of today will be available on YouTube probably tomorrow.
And the link, we get it from the...
And the link I will send, so these are all good questions. So I will send the link around tomorrow in an email that will ask you to complete a feedback form in order to get some feedback about how this course went, things that we can improve for the future, things you liked. And also, of course, if you want to get credit for attending today, credit towards our completion certificate that we're kind of working on, then you'll need to return the feedback form.
Okay.
So I'll send that around tomorrow.
Thanks.
Any other questions? Okay, well, in that case, thank you all very much for coming. Oh, that's not what I wanted to do.
I might have a last question, sorry.
Sure.
Today we used your session of Jupyter Lab. So since we now registered and we can have our own, in order to make it work for today, we just have to copy paste your environment, or we...
Right, okay, so there's 2 things that you can do. So one, you can, so these BinderHubs, whether it's the KAUST BinderHub or the public BinderHub, are they're always available. So if you go back and click on those links on the GitHub repo, like they'll work tomorrow or next week or next month, they should work more or less indefinitely. So that would be one way, like in the very near term. The other option is on the setup instructions for today's lessons.
Yeah.
Kind of walks you through how to install mini Conda locally on your computer.
Yes.
And so there's video tutorials for Windows and Mac, and I walk through Linux a little bit here. So there's instructions for how to install that. And then to get started with creating the software environment that we used, the best thing to do would be to look at this Getting Started with Conda episode that I kind of walked through at a very high level, because we already had the environment created. But this explains in detail how to create the Conda environment locally with the software that we use today, basically. Okay.
And is there any limitation when we work in Jupyter Lab compared to on the shell, on the terminal? I just think about that, like, for example, when as a comparison to using R on the terminal or how is it called?
RStudio?
Yeah, RStudio, sorry. Yeah. Like, would we be somehow limited in the amount of data we can load or things like this?
Right. So basically the question there is it kind of, it depends. So RStudio so Jupyter Lab is like the Python version of RStudio in the R community. Basically, like how they would relate to one another. Now, obviously, if you're running Jupyter Lab locally on your workstation or your laptop, also Conda is available on the Research Computing IT's remote scientific workstation. Mm-hmm. So you can also use this on the remote scientific workstation. There, you're just going to be limited by the resources that you have available, obviously, on those machines. Now, you can run Jupyter Lab and you can run RStudio directly on top of Ibex, and get access to whatever resources that you would need for Ibex. Now there's some caveats to that, but it can be done, and I often do it. Exactly the mechanics of doing that are a bit more advanced and beyond the scope of this kind of intro course. But we are in some kind of discussions about the best way to kind of make those things available, or make like how to do that available. So one of the things that we're considering doing is just some short webinars, like 15 or 20-minute webinars that we put on YouTube. Not necessarily like live trainings like this, but more like I would make a video of how to run Jupyter Lab on Ibex, or how to run RStudio on Ibex, and just chuck it up under the YouTube channel, and then people could kind of follow along with the example that I have there. So things like that. So it would be useful in the feedback form that I send around tomorrow. If you can think of things like that you would like to know how to do, there's a kind of a catch-all question at the end of the feedback form that you can just put in those kinds of requests, and then I'll look them over with my colleagues, and then we can think about how best to get answers to those kinds of questions.
Okay, good, thanks.
Okay, any other questions? Okay, I guess not. Well, thank you guys very much for coming. Thank you, Glendon, for staying around all day to help out with Q&A and things like that. It was very, very helpful. Thanks again to the Research Computing IT team for the excellent Chaos BinderHub, and to the MyBinder team, the BinderHub team that puts together the public BinderHub that makes these kinds of trainings kind of possible. And maybe I'll see some of you next Tuesday afternoon for the training on Git. Okay.
Oh, thank you.
Bye, guys. So I'll hang around. I'm going to stop recording, but I'll hang around for a few more minutes if there's any questions or anything like that.
Awesome. Hey, David.